Yes. Today we're starting with a very, very important topic. Very important topic. And this is NER and ST. NER-NST, Nernst equation. At least in board exam, you can 90% expect there will be a numerical on Nernst equation. Even in competitive exams, numericals are generally asked on Nernst equation. See, last time I told you about standard reduction electrode potential value, standard REPV. What's the meaning of standard? Standard means there are three conditions which will make an electrode standard. Standard temperature of 25 degrees centigrade, standard concentration of ions which should be 1 molar, and standard pressure means if any gas is involved, then pressure of the gas should be 1 atm. If all the three conditions are standard, electrode is standard, its reduction electrode potential value is also standard, that is standard REPV. But if there is deviation in any one or more conditions from the standard ones, then reduction potential of the electrode will change. And what is the changed, what is the deviated value from the standard value, that we can calculate by using Nernst equation. So it means we can say Nernst equation is used to calculate non-standard REPV, or we can say REPV of a non-standard electrode. Right? Now, write down. REPV of an electrode depends on number one, concentration of ions. Number two, concentration of ions. Number two, temperature. Number three, pressure of the gas. Pressure of the gas. If temperature is 25 degrees centigrade, concentration of ions is 1 molar, and pressure of the gas is 1 atm, it is a standard electrode, and its reduction potential is standard reduction potential, standard REPV. Any change in concentration of ions or T or P or temperature or pressure changes REPV of the electrode which is calculated by using Nernst equation. By using Nernst equation. Write down the equation. E m plus n oblique m. If I say Fe plus 2 and oblique Fe, so this is m plus n, value of n is plus 2 in this case, and Fe. So E mn plus oblique n is equal to E naught m plus n oblique m. So far, this is non-standard REP is equal to standard REPV plus RT divided by NF ln. Ln, you know, is natural log. Concentration of ions of oxidized species. It means if I say Fe plus 2 oblique Fe, oxidized form will be Fe plus 2 and reduced form will be Fe. So divided by concentration of reduced species. But I'll take one more example. Let us say electrode is ferric ions and ferrous ions. Oxidized form is Fe plus 3, reduced form is Fe plus 2. Right? Write down. Within brackets, write down concentration of any solid will be taken equal to 1. Or I can say non-standard REPV is equal to standard REPV plus. I'll convert natural log to the base 10, for which I'll multiply by 2.303. Value of R is 8.314. Temperature 298 Kelvin. I'm taking standard temperature, that is 25 degrees centigrade. But in case a temperature other than 25 is given, then you have to accordingly substitute. Divided by N is number of electrons transferred, which I'll tell you when we take up the example as numerical. F is Faraday constant. Faraday constant is 96,500 coulombs. Log, now this is log to the base 10. Concentration of oxidized species divided by concentration of reduced species. Finally, non-standard REPV is equal to standard value plus value of this part you will remember. This will be 0.059. 0.059 divided by N is number of electrons transferred, log concentration of oxidized species divided by concentration of reduced species. I think this is equation number 10 or 11. I think should be 10. Label it. I've labeled it equation number 10. Rather, this one. Wait a minute. Label this one as equation 10A and this as 10B. Even this equation will be important. What will be the importance of this equation? I'll tell you. First, let me finish this part. So final equation, numbering 10B. If you look at this equation carefully, this I'm clarifying because in most of the schools or coaching, this probably topic might have been over and you might have been taught here in negative sign. It's okay. You can use negative sign. If you use negative, then it will be log reduce concentration of reduced species divided by oxidized species. But if I use, because I'm in the habit of using positive sign here, if it is positive, then oxidized divided by reduce. Doesn't make any difference. That's up to you. Now coming to this equation, what is the importance of this equation? This equation will help you in handling theoretical questions. If the question is, for a particular electrode, I want to increase reduction potential or I want to decrease reduction potential. How can I do that? I said for a particular electrode. If I want to increase or decrease REPV, how can I do that? These are two things. Reduction potential directly proportional to temperature, directly proportional to concentration of oxidized species. So I can increase reduction potential of any electrode by increasing temperature or by increasing concentration of oxidized form or by decreasing concentration of reduced form or by making all these changes, right? So that's how you should be able to handle the question. I'm sharing one numerical. We'll solve this. Yes, here it goes. This is numerical number 8. You'll find this as numerical number 8 in the video. Videos are, of course, not being uploaded these days. Will take time. Yes, numerical is calculate REPV with electrode so and so given E naught aluminium is this. So it will be E aluminium is equal to E naught aluminium, that is minus 1.66 plus log concentration of oxidized form is aluminium ions and the concentration is 0.1 divided by reduced form is aluminium solid and the concentration of any solid is 1. So when you solve, you get the answer. It will be minus 1.6797 volt. I'll suggest you one thing. Whenever there's a numerical on Nernst equation, calculate up to 4th decimal place because changes in values are very small in reduction potential values. So this is Nernst equation for an electrode. But you know, a cell consists of 2 electrodes. If I want to apply Nernst equation for the cell, one way is I calculate reduction potential of both the electrodes separately. And after that, I use the formula E cell is equal to E right minus E left. Naturally, that will take time because two cumbersome equations, calculations will be involved. Third will be very simple. We'll have to calculate the value of two non-standard electrodes. Then, of course, difference of the two. But we can use Nernst equation for the cell and we can calculate the value of non-standard output of the calculate output of the non-standard cell directly. So next topic is heading right down calculation of cell potential of a non-standard cell. Non-standard cell. See, what is a standard cell? Standard cell is the one in which both the electrodes are standard. But if one of them or both of them are non-standard electrodes, then naturally cell will be a non-standard cell. Right on. If one or both the electrodes, if one or both the electrodes of the cell are non-standard, then the cell potential can be calculated. Then the cell potential can be calculated by using Nernst equation as given below. By using Nernst equation as given below. Wait a minute, let me take the attendance. Yes. Please copy from the board. Say balanced cell reaction, say the balanced cell reaction is AA plus BB gives CC plus DD. Quite obvious, small letters ABCD represent stoichiometric coefficients. Capital letters ABCD represents formulas of reactants and products. Now, according to Nernst equation, E cell means EMF of the non-standard cell is equal to E naught cell, that is EMF of the standard cell, plus 0.0592 divided by N log concentration of A to the power A, B to the power B divided by C to the power C, D to the power D. Very important equation. Again, if you are used to a negative sign here, go ahead, doesn't matter. But if you're using negative, it will be log CCDD in numerator, AABB in the denominator. I have written this equation on the basis of a balanced cell reaction. I'll give you 4 examples in the form of numericals. That is, we are going to solve 4 numericals, right from simple one to maybe slightly may appear difficult for you, and tell you how do we write the equation. Number 2, how do we balance the equation? Then how do we decide the value of N? I'm sharing all the 4 numericals together because I'll have to share them again and again otherwise. Wait a minute. That you can check. These are numerical number. Check out what's the message. These are numerical number 9, 10, 11, and 12. In the video also, these will be in text numerical number 9, 10, 11, and 12. I'll solve these numericals one by one. Ninth, calculate EM of the cell, zinc/zinc ions. Concentration is 0.4 molar. Saltbridge, copper ions, 0.6 molar copper solid, right? This is the cell notation given, and we are given E naught zinc and E naught copper values are given. That is, standard REPVs of both the electrodes are given. First of all, how do we write balanced chemical equation on the basis of notation given? Listen to instructions very carefully because numerical is almost a must in the numerical in the exam, and it's not a difficult numerical, simple to solve. How to write the equation? Second part will be balancing. Before single slash are reactants. This and this zinc atom, copper ions, they are reactants. After the single slash are products. It means products are zinc ions, copper atoms. So equation, zinc plus copper ions. Products will be zinc ions plus copper. This equation is already balanced. So balancing part, I'll tell you in the second example, that is numerical number 10. I'm directly applying Nernst equation. E cell will be E naught right minus left. Right is copper, left is zinc. E naught values of both the electrodes are given. So it will be copper is 0.34 minus Zinc is minus 0.76. This is E naught cell plus 0.0592 divided by N. Again, this is a simple example. Value of N will be, listen carefully, stoichiometry is 1111. Number of electrons transferred in any one reactant. Number of electrons transferred in one particle of any reactant. 2 electrons. Multiply by its stoichiometry. So transfer of 2 electrons multiply by 1. Or I can say, in case of copper also, transfer of 2 electrons multiply by stoichiometry, that is 1. Value of N will be 2. Log AABBCCDD. This is solid. Concentration will be 1. Copper ions 0.6. Raised to power stoichiometry is 1 divided by zinc ions. Concentration is 0.4. Raised to power stoichiometry is 1. Copper is solid, therefore 1. When you solve, you'll get the answer as given in the WhatsApp message. This will come out to 1.1052 volt. Second, calculate EMF of the cell of the following cell. Cell potential, E naught cell is directly given. And the cell is zinc solid, zinc ions aqueous, 0.4 molar, salt bridge. This is Fe plus 3. How much? 0.6 molar slash Fe plus 2. This is 1.2 molar slash platinum. In this numerical, there are 3 concentration terms involved. One thing more, look at the notation very carefully. In the cathode, that is right electrode, we have ferric ions slash ferrous ions, and at the extreme right is platinum. See, when do we write platinum as an electrode? Sometimes we write, sometimes we do not. I've written platinum on the extreme right, I'm not written on the extreme left. See, out of these two, one is reactant and the other is product. If none of the two is solid, I'll repeat, if none of these two is a solid, then we use platinum as an inert electrode, because the reaction will take place on a solid surface. Reaction will take place on a solid surface. And if none of the two solids is present, then platinum is used to provide surface for the reaction to take place. Platinum will not take part in the reaction. Now, the first step, we'll write the equation. Reactants are zinc, Fe plus 3. Products are zinc ions and Fe plus 2 ions. Second step, how do we balance the equation without wasting time and without any mistake? Listen very carefully. Zinc. In one zinc, there is transfer of 2 electrons. In one zinc, there is transfer of 2 electrons. Therefore, 2 becomes the stoichiometry for iron on both the sides. So this is 2 and 2. And vice versa. Means what? In one iron, I'm saying one iron. In one iron, there's transfer of 1 electron. Therefore, 1 will be the stoichiometry for zinc on both the sides. 1 and 1. Now you can check. Equation is balanced in terms of number of atoms or ions and total charge. Very important part is total charge. On the left hand side, total charge is 3 2s are 6. On the right hand side, charge is 2 plus 4, 6. Equation is balanced. Now we have this equation in the form AABB gives DD. Now we'll use Nernst equation. E cell is equal to E naught cell is directly given 1.53. Plus 0.0592. Now listen to the value of N very carefully. Although I told you in the previous numerical also, number of electrons, and that you should cross check with both the reactants, right? Number of electrons transferred in one zinc, 2 electrons, multiplied by number of zinc, that is multiplied by stoichiometry. Or if you want to try with iron, iron is changing from Fe plus 3 to plus 2. When it changes from plus 3 to plus 2, there's transfer of 1 electron. So transfer 1 electron multiplied by stoichiometry, value of N will again be same. And I advise you to cross check the value of N by using both the reactants. First, you try to calculate N with one reactant, and then by using the other reactant. Value of N is 2. This is solid. I'm not writing. This is 1. Fe plus 3.6 raised to power 2 square. Zinc ions 0.4 raised to power stoichiometry is 1. And Fe plus 2 ions 1.2 molar raised to power stoichiometry 2. This will be the answer. You can see in your WhatsApp message also. Answer will be 1.524 volt. Numerical number 11. Calculate M of the cell platinum Sn plus 2. Sn plus 2 is stannous. 2 molar oblique stannic Sn plus 4, 0.4 molar salt rich Au plus 3 gold ions 0.8 molar / gold. Equation. Platinum is again to provide surface for the reaction to take place. Sn plus 2, Au plus 3. Products are Sn plus 4 and Au, gold. Balancing. Tin. In tin, there is transfer of 2 electrons. So gold ke liye, it will be 2 and 2 on both the sides. Gold. In one gold, there's transfer of 3 electrons. So 3 and 3 is the stoichiometry for tin on both the sides. Must check in terms of atoms and in terms of charges as well. Total charge on the left hand side is 6 plus 6, 12. On the right hand side, it is 3 into plus 4, 12. Equation is balanced. Nernst equation. E cell will be E naught right minus left. Right is gold. Gold is 1.52. Left is 10 and the value is 0.013 plus 0.0592 divided by. Can someone tell me what's the value of N?
6.
Yes, good. 10. Transfer of 2 electrons into 3, 6. Or you can say gold. In gold, there's transfer of 3 electrons multiplied by 2, that is stoichiometry. Value of N will be 6 log Sn plus 2, 2 molar cube, gold ions 0.8 molar square. divided by Sn plus 4, 0.4 molar cube, and gold is solid. This is 1. Rest is calculation. We'll get the answer. This will be 1.5257 gold. Although in the exam, you'll be given the value of log, and from the log value itself, you get an idea what should be your substitutions. Still, this is the way. Last example will be slightly typical. Calculate EM of the cell, aluminium ions, 0.4 molar, salt bridge, I2 solid, iodide ions, 0.5 molar. Electrode potentials are given, that is different, right? Reactants are aluminium and iodine, I2. Products are aluminium ions and I minus. Listen carefully, because balancing for you may take time. And if balancing is wrong, everything goes wrong. First of all, make number of atoms equal on both the sides. First of all, balance atoms. Iodine on the left, there are 2 atoms. On the right, there is only 1 iodine. What you should do is, because we are balancing in terms of number of electrons transferred per particle, here per atom or per ion. So it's better I use half on the left. Better I use half on the left rather than I use 2 iodide ions on the right. Now, iodine is balanced, aluminium is already balanced. Now, in aluminium, there's a transfer of 3 electrons. So 3 will be the stoichiometry for iodine on both the sides. 3 times will be 3 by 2, and this will be 3. In 1 iodine, there is transfer of 1 electron. Stoichiometry is 1 and 1. Although on the left-hand side, both are solids, concentration of solids will be 1, and 1 raised to power 3 by 2 will not make any difference. Calculation will be easy, but make sure you convert this into whole number stoichiometry. And to convert into whole number stoichiometry, multiply the entire equation by 2. It becomes 2, 3, 2, 6. And finally, you should check whether the equation is balanced or not. Now, this is AABB gives CCTD. Coming to Nernst equation. E cell is equal to E right. Right is iodine. Iodine is 0.54 minus aluminium is minus 1.66 plus 0.0592. Yes, value of N last time.
6.
6. Log. Both reactants are solids, 1 into 1. Raised to power anything doesn't make any difference. Aluminium ions 0.4 square. Iodide ions 0.5 raised to power 6. This will give the answer. This is 2.2256 volt. 2.2256 volt, yes. So that was Nernst equation. As I said, a very, very important topic in a syllabus. Okay, coming to next topic. Heading is effect of external potential on galvanic cell. Effect of external potential on galvanic cell. If you remember, I told you the working of galvanic cell, electrochemical cell. There I had taken the example of Daniell cell. Left hand side was zinc vessel, that is zinc electrode. Right hand side was copper vessel, that is copper electrode. And during the process, oxidation takes place at zinc, reduction takes place at copper electrode. Electrons flow from zinc towards copper, and current flows in the reverse direction, that is opposite direction by convention. Let us say these are two people, two persons, two boys, let us say, and after school, almost every day they fight. This fellow is stronger than this one. He pushes him this side. Every day this thing happens. Now, one day he gets annoyed. He says, no, I'll have to do something. He tries to push him, although he has been trying in the past also. He starts going to gym and builds body, and he starts applying pressure in the opposite direction, naturally a little more now. Effect now has decreased. He gradually increases his strength. This effect will decrease, and a stage will come when both are equally strong and net result is zero, neither pushing this way or this way. But if this fellow continues to strengthen himself, then the process will start again, and now the process will start in the opposite direction. Exactly same type of topic you're going to study now. Zinc copper electrode electrochemical cell that has an output of 1.1 volt. If we apply an external electric potential which is less than 1.1 volt and we gradually increase it, cell will still keep on working, cell will still keep on giving output so long as external potential applied is less than 1.1 volt. But when external potential becomes equal to 1.1 volt, then cell will stop giving any output because the reaction will be at equilibrium, in fact. Now, if we further increase external potential, process will start again, and now the process will take place in the opposite direction. When I say opposite direction, it means now the reaction will take place in a non-spontaneous manner. Why in a non-spontaneous manner? Because now the reaction will take place in the presence of external source of energy. And cell reactions will be reversed. Cell will now behave as an electrolytic cell. Copper will be oxidized now. Zinc ions will be reduced. Electrons will now flow from copper towards zinc. Current will now flow in the opposite direction. So this will be a totally theoretical topic, that this is the output. If we apply external potential this much or that much, what is going to happen? Very simple topic that way. Right on. Consider the galvanic cell, zinc ions slash salvage copper ions slash copper. Under standard conditions, output of this cell is 1.1 volt. So if an external potential is applied in the opposite direction and it is gradually increased. It is gradually increased. Reaction will continue to take place. Reaction will continue to take place till the opposing potential applied is less than 1.1 volt. When opposing potential becomes 1.1 volt, reaction will stop and, in fact, doesn't stop, it is at equilibrium. Reaction will stop and no current will flow. If external potential is further increased, reaction will start again. Reaction will start again, but in the opposite direction. Cell will now behave as an electrolytic cell in which non-spontaneous reaction will take place with the help of electrical energy. Copper atoms will be oxidized, zinc ions will be reduced, electrons will flow from copper towards zinc electrode, and current in the opposite direction. Now, for today, a very small topic, one more very, very small topic, right on the heading, concentration cell. Concentration cell. Look here on the board, there is a cell written on the left hand side, that is anode is zinc electrode or zinc redox couple, and cathode is copper couple. What happens if we take cathode as well as zinc redox couples, or both are copper redox couples? Is that possible? This topic is related to that only. Yes, the answer is yes. We can have both the electrodes made up of same redox couples. The only thing is their concentration of ions in these two electrodes should be different. That is why the heading is concentration cell. Right on. An electrochemical cell made up of same redox couples as cathode and anode with different concentration of ions is called a concentration cell. is called a concentration cell. It will have a net cell potential if the concentration of oxidized species in the right half cell means cathode, in the right half cell is more than in the left half cell. For example, zinc solid slash zinc ions 0.4 molar, salt rich. Zinc ions on the right hand side, concentration should be more than 0.4 molar. 0.6 molar slash zinc solid. That's all about this topic.